Now let's take a look at some logarithmic equations and how we might go about solving those. And we'll do this in a similar way. We have a couple examples here. We'll outline some general steps and we'll do those steps in these examples. Now, for these logarithmic equations, the general strategy is first you want to write the equation as log base something. It doesn't matter what the base is. So in this example, it's going to be 9. In this second example, it's going to be log base e. But log of some base equals some number. And a lot of times, this may require log properties. So may require log properties. Then you'll apply the definition of the log. And of course, we're going to do these in this example, so if you don't know exactly what I mean, don't worry too much. Then the result will be some equation that you know how to solve. So solve the resulting equation. And depending on the problem, the resulting equation, again, it could be linear, it might be quadratic, just depends on the problem. So let's see what this looks like in the context of these problems here. So for this part A problem, notice I don't have log of one thing equals a number. I have two logs being added together. However, I can combine those two logs using the multiplication property of the logarithm. So going to another page here, in part A, this is going to be equal to log base 9 of the multiplication of these two terms here, which is x minus 5 times x plus 3. And that's going to be equal to, well, let's see, 1. So now I have that log of a single thing as opposed to two logs being added together, as is done here, equals 1. And so now I've done my first step here. Now I'm going to apply the definition of the log. Another way you could rephrase it to say the exact same thing is convert to exponential form. So log base 9 of something equals 1. In exponential form, the thing that you're taking the log of, in this example, x minus 5 times x plus 3, would have to be equal to, remember you bring the base over here and this becomes the exponent. So 9 to the 1. What we have as a result here, after applying the definition of the logarithm, is a quadratic equation. It's quadratic because this left-hand side, if you distribute it out, you get x to a second power. Now, if this right-hand side was 0, it would be a very easy quadratic equation to solve because we just set x minus 5 equal to 0 and x plus 3 equal to 0 and get our answers. However, the right-hand side is not 0, and so in order to solve this quadratic equation, we're going to have to distribute this left-hand side and then move the 9 to the left-hand side from the right-hand side and solve from there. So distributing on the left-hand side, or foiling if you will, gives me x squared minus 5x plus 3x, that'd be minus 2x, minus 15 equals 9, and we'll go ahead and subtract 9 now from both sides, and we get x squared minus 2x minus 24 equals 0. Now I can factor this. If you couldn't factor, you could apply quadratic formula, but this actually factors as x minus 6, x plus 4 equals 0. And this means that x equals 6 or x equals -4. And that's almost the end of it. It turns out that with these logarithmic equations, sometimes you can introduce what's called an extraneous, or sometimes it's called an artificial solution. So something that looks like it should be a solution, but it's actually not. Now at the end of this video, I will say why such things happen, but for now, let's just imagine we wanted to check our answer for this x equals -4. So if I take this -4 and I put it back into my equation, then I should get something that's true. That's what it means to solve an equation, right? When you put the x value back into your equation, you get something that's true. However, what happens here is if I put -4 in for x, well, this x minus 5 term would become -9. And log of -9 is not defined. So it can't be a solution. So -4 is not a solution. You can go ahead and check 6. It turns out that both of these logarithms are defined for x equals +6. 6 minus 5 is 1, and 6 plus 3 is 9. So the x equals +6 solution works. So in essence, once you've done these 3 steps that I've seen here, there's actually one more step to do, and that is to check to make sure your answers make sense. So let's go ahead and write in exactly what that means. What that means is we will discard any solution which causes you to take the log of a negative number, or more precisely, a number less than or equal to 0. So in this case, this -4 solution, I like to think of them as fake solutions, will not count as a solution, since when we put -4 into the original problem statement, we are taking logarithms of numbers that are less than or equal to 0. Now, one more subtle point here. Notice that we didn't say that the solutions can't be negative. As a very brief example, think about the equation ln of -x equals 0. So the first step of making sure you have log of something equals a number that we wrote is already true. Then we apply the definition of the log. We get that -x equals, remember the base here for ln minus x equals 0, the base is e, so this would be e to the 0, which is 1, and then we solve for x, we get x equals -1. When you ask yourself, is x equals -1 a solution, we check our answers. If you put -1 in this equation, then you are doing ln of -1, which is ln of 1. So you're not taking the logarithm of a negative number. So x equals -1 would in fact be a solution. And again, the point here is make sure you don't just discard all negative solutions. You have to put them into the original equation and see, am I taking logarithms of negative numbers?